applications to Soergel bimodules. Take it away, Vanessa.
Okay, first of all, thank you very much for the invitation to this workshop, despite the fact that I can't say I enjoy being here because I'm just at home, but I'm enjoying the talks. So yeah, so what I want to talk about is some sort of abstract categorified representation theory and some applications of that to Soergel bimodules. So firstly, why are we, and why is this not working? Why are we studying abstract two-representation theory? So the idea is that we want to provide abstract methods that can then be applied to any example in categorification. So we don't have to study categorical actions of Lie algebras and separately study actions of Soergel bimodules and prove the same things over and over again. So, and then of course we want to apply these results to the examples that people are hopefully interested in. So just some general notes. So for me, K is an algebraically closed field, and later on for Soergel bimodules, it will be the complex numbers, because unfortunately at the moment we can't say very much outside that. And moreover, when I talk about categories, what I mean is small categories, or at least locally small. So whenever I mention a category that's not small, you should replace it by an equivalent small category. Okay. So we want to classify simple two representations in some sense, yeah? Because if you study representation theory, then the first thing that you, when you teach undergraduates about modules, the first types of modules that you tell them about are simple modules. And so if you have some finite dimensional algebra, how do you go about finding your simple modules? Well, you could try decomposing your identity into primitive orthogonal idempotents. And then those have some kind of equivalence relation on them, which here I want to phrase as they're equivalent if they, when you factor out the Jacobson radical, end up in the same, so then you have a product of matrix rings. Remember, we have an algebraically closed field, so we're just matrix rings over the field. And if two idempotents are equivalent if they end up in the same matrix ring. Okay, so now we want to pick a set of representatives with respect to that equivalence class. And then we can look at the quotients of our projectives AEI modulo the radical, and that will give us a simple module. And these simple modules form a set of representatives of isomorphism classes of simple A modules. Moreover, if I look at the endomorphism ring of this simple module, well, that's the centralizer algebra EI AEI modulo the radical, and that's just the field because that's a local algebra, and yeah. So this is Schur's lemma, yeah. So nothing very exciting is happening, but we also have a double centralizer theorem where we can describe the endomorphisms of SI over its endomorphisms, and that's just A modulo the annihilator. And if we look at this, then that's again just this matrix component in the Wedderburn decomposition, and that's Morita equivalent to the actual endomorphism ring, which was the field. Yeah. So this is all really well known, and you can teach it in a third year module or something. Or whatever your introductory course in representation theory, whatever year that's taught. Okay. So now the upshot is that all of this in some form categorifies, but not at all on the nose. Yeah, things become much more difficult. So we don't have anything like a radical that we can quotient out by and get something semi-simple. Then we do get some kind of analogs of matrix rings, but they can have lots and lots of simple modules suddenly. And endomorphism rings of simple modules can be very far from trivial, and so on and so forth. Yeah, but we can get some sort of analog of this. Okay, in order to do that, so what do I want to categorify this to? Well, an algebra is a category with one object, and the elements are just the endomorphisms of that object. Or if I have my nice decomposition into primitive idempotents, I can say, well, it has objects 1 up to n, and my maps from I to j are just, well, ej, aei, or ei, aej, whichever you prefer in terms of opposites and left or right actions or whatsoever, and so on. Yeah, so we can view our algebra as a category, and then a representation of the algebra is just a functor from that category to the category of vector spaces. We associate our module to our single object, or we associate the corresponding subspaces of the module to the idempotents, and our element of the algebra, which is an endomorphism of our object, goes to some linear transformation of the linear endomorphism of the vector space. So now the categorified version is that we have a 2 category rather than our algebra, which is a category. We have a 2 category, and so that consists of, I mean, so I think most people at this conference are familiar with this, but I want to set up some notation. So this consists of a class, or if we're lucky, it's a set, but that bit could be a class of objects. Then for every pair of objects, we now have a category of morphisms. So rather than just having a vector space of morphisms, we now have a category of morphisms. So that is objects, which are called 1 morphisms, and morphisms, which are called 2 morphisms. And of course, we can, since this is a category, we can compose such 2 morphisms, and we have identity 2 morphisms, and so on and so forth. However, we also need to be able to compose horizontally. So we need some kind of functorial composition that takes us from the product of 2 composable morphism categories to the composed thing. Yeah. So that is some extra data. And then we need, because in a category we need identities, we need identity 1 morphisms. And then we need some axioms which ensure that this functorial composition is associative and the identity 1 morphisms really act by identities. And so they really behave like identities. And also the only other axiom is, that we need is, we need to make sure that if we can compose morphisms in here, and we can compose morphisms in here, and we can compose them horizontally to push them over. And those things have to be nicely compatible. So that's a 2 category. If I say, well, rather than wanting strict associativity and strict identities, if I just ask for some isomorphisms or just some morphisms, then I get a bicategory. And that's, so I will mainly talk about 2 categories, but everything I'm going to say will work the same for bicategories. It's just you have to carry a lot more notation around, so I'm just avoiding it. Okay, so here are some examples. So I said most people here will be familiar with 2 categories, but those who are not are surely familiar with monoidal categories, given that the conference title is something like, I've forgotten it, but it's something like representations of monoidal and 2 categories or something like that. So if I have a monoidal category, that's a bicategory with 1 object. And the objects, so what people who work with monoidal categories call their objects are the 1 morphisms in this 2 category. And the morphisms in the monoidal category are the 2 morphisms in the bicategory. And if the monoidal category is strict, then that's a 2 category. The other example that everybody is very familiar with is cat, which has objects, small categories, 1 morphisms, any old functor, and 2 morphisms, any old natural transformation of functors. So that's a really, really, really large and floppy 2 category. But essentially everything that I will say, all the 2 categories that I ever work with live inside cat. Okay. And then here's the 2 category that will play a big role here, because it replaces the category of vector spaces in normal representation theory. So I said a representation of an algebra is a functor from our algebra viewed as a category to vector spaces. And so what replaces vector spaces here? That's this two category, which we call AKF. A for additive, K is our field, and F for finitary. So the objects are small idempotent complete K-linear categories, which have only finitely many indecomposable objects up to isomorphism, and where all morphism spaces are finite dimensional. So this is a very technical thing, but what you should think of is it's the category of finitely generated projectives for some finite dimensional algebra. Yeah. So you take your algebra, you take all you find the idempotents, you take all the AEI, for EI is some idempotent, and you take their direct sums, and that's your category. And then one morphisms are additive K-linear functors, because we now have this nice K-linear additive structure. Sorry, that should have said additive. Additive is missing here, I think. Too many adjectives. So so now we want additive functors, and two morphisms are just any natural transformation of these functors. So we don't restrict two morphisms ever. Okay. So now so we want to study some kind of analog of finite dimensional algebras. Yeah, so the analog is a finitary two category, which has finitely many objects. And each of our CIJs is, so previously, if you think about finite dimensional algebra and you have some idempotents and you associate some objects, then the EI, AEJ are finite dimensional vector spaces. And so here we want our equivalent, we want one of these categories of finitely generated projectives over some algebra. Then now that we have this nice additive and K-linear structure, we want that preserved under composition. That's a very natural thing to require. And we want our identity one morphisms to be indecomposable. And that's not really crucial. It just makes life a bit nicer, because it just somehow pins things down more. It's like having an idempotent decomposition of your identity in your algebra, which makes the algebra somehow more tractable because you have more information. But it's not really super important. So I've kind of said this already, that those are meant to be two analogs of finite dimensional algebras. And now lots of the interesting examples that come out of representation theory actually have a Lie theoretic background, and those are usually algebras that have some kind of involution, simple preserving involution. And that categorifies to bi-adjunction. So a two category is fiat if it's finitary, and moreover, we have some involution that takes adjoints, morally speaking, but it's supposed to be involutive. So F double star is supposed to be isomorphic to F star. And so we have a weaker concept that's weakly fiat, or we've just renamed that into quasi-fiat, but where this is not involutive, where we have left and right adjoints, but they don't necessarily have to agree. So that's a fiat 2 category, and examples are, so tensor categories, they're usually only weakly fiat because there's no reason why left and right adjoints should agree. Fusion categories are semi-simple tensor categories, so they're quite well studied. Those are examples. Then we could take A modules and take what we call projective endofunctors. So what we mean by that is, well, we need the identity functor, and apart from that, we take functors that are isomorphic to tensoring with projective bimodules. And that's always finitary. It's weakly fiat, so it does have left and right adjoints if the algebra is self-injective, and left and right adjoints agree if the algebra is weakly symmetric, which means that the top and socle of the projectives are isomorphic. Okay, then we have, so now we get to the categorification motivating examples. So certain quotients of Kac-Moody 2 categories fall into this framework. And Soergel bimodules fall into this framework, provided we work over the coinvariant algebra rather than the full polynomial ring. Okay, so since Soergel bimodules are the motivating example, I want to talk about them a bit more now. And before I can talk about Soergel bimodules, I need to talk about Hecke algebras. So to get a Hecke algebra, we take a Coxeter group. So that's a pair of the group together with the set S of simple reflections. And it has this nice presentation that simple reflections, well, they're reflections, they square to 1. And you can associate some integer to every pair of simple reflections, such that Sij to the power of that integer is the identity, and those are all your relations. So that's the Coxeter group, and then we can get the Hecke algebra, which is a quantization of the group ring. And this has I don't want to set up notation for this because I'm not going to need it, but it has the Castellan-Lustig basis, and that leads to the cell theory. And Torge explained, was that yesterday? Yes, that was yesterday. So he gave some examples, and we'll see that reappear later on. So we do get some cell theory, and if we take a two-sided cell, or what we call an H cell, which is the intersection of a left with its dual right cell, then we can associate, or Lustig associated the asymptotic algebras to that, which are somehow, so the Hecke algebra is a quantization, so it has some parameter Q floating around, and we can, so these algebras are obtained by looking at the Hecke algebra, looking at the structure constants with respect to the Castellan-Lustig basis, and then letting Q go to 0. Okay, so these are these asymptotic algebras, and the reason why they're interesting is because they're, as you let your two-sided cell vary, and you look at the simple representations, those are in bijection with the simple representations of the Hecke algebras. Or you could, rather than just looking at all the AJ, where J runs over two-sided cells, you could look at the AH, where H just runs over one diagonal H cell in each two-sided cell. And then you can get all simple representations of the Hecke algebras. And the idea is that the asymptotic algebras are much simpler to understand because they're essentially just matrix rings, except you've modified your multiplication. If you multiply two matrices, you always have to stick the same matrix in the middle. But it turns out that doesn't affect the classification of simple modules. So these asymptotic algebras are helpful in finding simple modules for the Hecke algebra. Okay, so now we want to, and essentially we can, the thing is that all of that has been more or less categorified. So what are these Soergel bimodules? So now I will stick to a finite Coxeter system with a reflection representation, because so outside finite Coxeter type we can't say anything yet, just like we can't say anything outside complex numbers, which is why I let R be the coinvariant algebra over the complex numbers. Yeah, so this is the quotient of the symmetric algebra of our reflection representation, the vector space underlying the reflection representation, by the total invariance under the action of the induced action of the Y group, because since W acts on V, it acts on the symmetric algebra associated to V. And so we take the total invariants and we take the ideal generated by those of positive degree. And that's the co-invariant algebra, which is also the cohomology ring of the flag variety. So now we look at this co-invariant algebra, tensor it with itself over the invariance under a simple reflection. Yeah, so we've killed the total invariance, but of course we can still take invariance under particular elements of W. And that gives us this tensor product. And of course, that's an RR bimodule. So now the 2 category of Soergel bimodules, or the Hecke 2 category, has one object. So I could just talk about monoidal categories, but then I would need to reformulate all of our abstract results in that language. So this is one object which we identify with graded projective R modules. And one morphisms are shifts of direct summands of direct sums of finite tensor products of these Ri. Yeah, so we take the Ri, we tensor them together, we shift them around in our grading, and we yeah. And okay, I've written endo functors isomorphic to that because I want to make things strict. Because if I just take the bimodules, I just get a bicategory. And it's just a bit nicer to work with the 2 category, but the gray bit you can happily ignore. Okay, and 2 morphisms are just natural transformations of these endo functors, which is the same thing as bimodule morphisms between those Soergel bimodules. Okay, and now the categorification theorem is that indecomposable one morphisms are labeled by W, and this really categorifies the Hecke algebra. So there's this tensor product of bimodules. If you look at the split Grothendieck group, induces the Hecke algebra multiplication, and the indecomposable one morphisms in this decategorification correspond precisely to the Castello-Stich basis elements. Okay, so that is now about Soergel bimodules. What time is it? I think, is this maybe a good time to take an early break? I think I probably still have 3 or 4 minutes, but I think this is maybe a better.
Yeah, this should be fine if you like.
Good. Because I can't see the clock on my computer while I'm in full screen mode, and my watch isn't as precise. But
yeah, that's fair enough.
So you need to tell me then when I should continue, right?
Yeah, of course. Actually, I have a small question on terminology. Where does the terminology Hecke 2 category come from? I've heard Hecke category.
Okay, so this is my own terminology, and I realize that as the very sole person in the world to use this, I am unlikely to convince people. But my point is that Hecke category sounds like it's just a normal category. So, and I mean, at least it would have to be a Hecke monoidal category, right? Or monoidal Hecke or something. But then what happens when you go to singular Soergel bimodules? Then that is a proper 2 category. And to me, it makes no sense to have Soergel bimodules and singular Soergel bimodules live in different worlds.
Yeah,
So I decided it should be Hecke 2 category, and I have decided to call it that.
My name is Ben Elias, and I support this message.
What did you say then?
I just said, my name is Ben Elias, and I support this message.
Oh wow! I'm very pleased because Jordi calls it the Hecke category, and I always thought, well, I have no chance against Jordi, obviously. But...
Well, I mean, like, because what does singular Soergel bimodules categorify is this one category, right? This
exactly
idempotent thing, which I don't know. People call the sure algebra, but it's really a category, and there's really. So I've been calling it the Hecke algebroid.
Yeah, and I mean, I think my point of view is that algebras are categories, and it doesn't matter how many objects they have. And just the same way, this is a 2 category, and it doesn't matter that it only has one object. So, yeah.
Yeah, I agree with you, Vanessa, but to keep Ben's analogy, I mean, if you want to win voters, it's not about being right, it's about having the right pitch, the right, the best sounding name. So there, I think Jordi might have a case.
Yeah, okay. I mean, you can, if you're more, well, the question is, are you more worried about precision or more worried about phonetics?
I posted a question to the chat, which someone else answered about your usage of op. And the answer I got back was that what you probably meant was actually co-op or op-co. That once you're up at the level of 2 categories, the Australians, and this is become, you're going to interact with people who learned Australian style terminology. Op refers to turn the 1 arrows backwards only, and co refers to turn the 2 arrows backwards only. And co-op is doing both, which is apparently what you were doing there at that one point.
Yeah, I know. I forgot to change that. I mean, I found out that apparently the standard terminology is co-op. To me, it makes. I mean, to me, op seems perfectly well defined. It makes it clear that you're reversing both because there are clearly 2 ops. But yeah, so I think in our paper we do write co-op. But this is somehow, yeah. And to be honest, I can never remember which of the co and which of the op refers to which. I have to.
Well, I mean, the easy way to remember is that op is the one that's used in 1 category theory, so it's reversing the 1 arrows, and then the other one is the one that gets added for bi-category or 2 category theory.
Okay. Okay.
Yeah.
I still find that confusing, but perhaps now is a good time to restart.
Okay. If I can. Okay. So the reason why I thought that would be a good time to take a break is because now I'm going to start talking about 2 representations, which I've kind of not mentioned so far. There's a message in the chat. I can't.
Ignore me.
Okay, well, okay. Okay, now I need to make the chat disappear before I can see my slides again. Okay, so I've said before, I mean, a representation of an algebra is a functor from the algebra to vector spaces, and similarly, a 2 representation is a 2 functor from the 2 category to something. And I've already said, and this is why I introduced this somewhat strange looking 2 category, but it is the correct replacement for vector spaces for the examples that we're interested in, because you should always represent in the thing that you're enriched over. Yeah, so the reason why we have algebras act on vector spaces is because when we view it as a category, the algebra is a vector space. Yeah. So, okay. And I don't, why is this not, anyway. Okay, so now, what does this mean to have such a 2 functor? It means that to every object, I associate one of my finite dimensional algebras and or the categories of projected modules over that. And to every one morphism, I associate an additive functor. And then to every two morphism, I associate a natural transformation between those functors. So that's a two representation. And so the word finitary refers to the fact that we're representing in this particular two category. Okay, so the example that determines where we have to represent is that we want to have the UNEDA embedding. Yeah, we want to have the principal two representation, which is just given by CI blank. So the two category where I represent should be whatever I'm enriched over, where if I plug in the J, I land in the right thing. Okay, another example is I was talking about these two categories of projective AA bimodules where we always have to add the identity, but those of course act on projective modules. That's kind of the defining two representation. And so those are some examples. And now earlier I talked about how to find the simple modules for an algebra. So what's the correct analog of a simple module for a two category? And this was actually, I mean, by now this is quite old. This is 5 years old or so. But this was surprisingly difficult to work out what the correct thing should be, because all the different characterizations of simple modules for algebras somehow categorify to slightly different things. And the correct thing to categorify is the statement that a simple module is one that doesn't have any proper factor modules. And so a two representation is simple transitive if I can look at all the underlying, at all the categories that I act on, and they don't have any ideals which are stable under the action of my two category. So that's a simple transitive two representation. And the reason why this is the correct categorification of simple is because it leads to some sort of sensible Jordan-Hölder theory. Okay. And of course, now that so if once you've agreed what the correct categorification of the notion of a simple module is, then it's a natural question to ask, well, if we have some two category, can we classify simple transitive two representations? And the answer is, well, sometimes we can. But we can always construct one particular class of simple transitive two representations. And to do that, we need cell combinatorics. So in representation theory, sort of Lie theoretically inspired algebras are very often cellular. And so for two categories, you always get some cell theory for free. So you look at the set of isomorphism classes of indecomposable one morphisms, and then you can define various partial preorders on that. You can say that, I don't understand. Okay, now I can go here. Okay. So we say that f is left greater than or equal to g if I can multiply g by something from the left and get f as a summand. Yeah, so somehow somehow it's f is left greater than or equal if it's sort of in the left ideal, yeah, in some sense generated by g. And then, of course, once we have a partial preorder, we can look at equivalence classes, and those are called left cells. And then we can do the same thing on the right. We can say, well, f is right greater than g, greater than or equal to g, if I can multiply g on the right by something and get f as a direct summand, and that gives me right cells. And the two-sided preorder is where I'm allowed to multiply on both sides. And then that gives me two-sided cells, which we also call J cells. So this comes from semigroup theory, because because somehow these isoclasses of indecomposable one-morphisms, they form a multi-semigroup, and in semigroup theory, Green's relations are just called L, R, and J. Okay, so here's an example, and this is the same example that Soergel presented yesterday, because it's sort of the smallest example where you can see something interesting, which is, so for Soergel bimodules, the cells that you get are simply the Castellan-Lustig cells. Yeah, so I mean, that's somehow, it wouldn't be, all the categorification stuff wouldn't work if there weren't this correspondence. So if we have a Coxeter group, the Coxeter group of type B, so that's just the dihedral group with 8 elements, then the cells are given by this picture, and I'm drawing them slightly differently from what Soergel wrote yesterday, because I want to, so these are the left cells, and he just wrote them in one line, but I also want to encode the right cells. Yeah, so we have, so in this picture, we have 3 two-sided cells, the one corresponding to the identity, the one corresponding to the longest element, and this big square in the middle. And the big square in the middle consists of 2 left cells, which are given by the columns, and 2 right cells, which are given by the rows. And then we can also introduce this notion of an H cell. So this is the intersection of a left and a right cell. Yeah, so the middle two-sided cell has 4 H cells. But we're mainly going to be interested in what we call a diagonal H cell, which is the ones on the diagonal. Okay. And so a two-sided cell is called strongly regular if every H cell in it has precisely 1 element. So here, the identity and the longest element, those two-sided cells are obviously strongly regular, but the middle one is not, because I have 2 H cells which have 2 elements. And this is going to be quite important on the next slide, because there is a lemma by Aronchan and Walter Mazurchuk that to every simple transitive 2 representation, you can associate an apex, which is the two-sided cell, which is maximal with respect to not being killed by your 2 representation. Or in other words, with respect to not acting by 0 on the categories. So this is called the apex. And what this means, of course, is that if you want to study simple transitive 2 representations, you can do that apex by apex. Because you can, yeah, because every simple transitive 2 representation has a unique apex. So you can, if you go through all the two-sided cells and find the simple transitive 2 representations with each apex, then you have all of them. Okay. And if we now, so now we fix our apex, and now we can fix a left cell inside this two-sided cell, that is our apex. And then we can associate the so-called cell 2 representation. That I don't want to go into how we construct this, but this is simple transitive by construction. So out of this whole cell combinatorics, we get a whole bunch of simple transitive 2 representations for free. And so what's really nice about these strongly regular two-sided cells, where every H cell only has 1 element, is that so if my apex is strongly regular, so every H cell in there has only 1 element, then any simple transitive 2 representation that's associated, so with that apex, is equivalent to a cell 2 representation. So in that case, so if we have a 2 category where all two-sided cells are strongly regular, then all cell 2 representation, all simple transitive 2 representations are equivalent to cell 2 representations. So that is, for example, true for appropriate quotients of Kac-Moody 2 categories. So this means, yeah, that the cell 2 representations, which are the ones where the underlying categories are the modules over the cyclotomic KLR algebras, that they really exhaust simple transitive 2 representations. Then it's also true for these 2 categories of projective bimodules that I've been talking about. Though this I, at some point, assumed when I introduced two categories, I think I forgot to say it, but it was on slide, that C is fiat. This was not necessarily relevant for all of this, but this theorem here really needs fiat. So we said two categories of projective bimodules are fiat only if, well, it needs weakly fiat, not fiat. So these are weakly fiat only if the algebra is self-injective, but even if the algebra is not self-injective, then we can show that simple transitive implies cell by other means. So, and moreover, if I look at Soergel bimodules in type A, then the cell combinatorics, the Cash and Lustig cells associated to the symmetric group are strongly regular. So again, we only have cell true representations. But this is not true in other types. And the problem is precisely because of non-strong regularity. Now, we just saw this example of type B2, where we're not strongly regular, and then things go wrong. So what do we do then? So firstly, now we have fixed our apex J that we want to find the simple transitive 2 representation to. Now we pick some left cell in it, and we look at the dual right cell. Yeah, remember we have this involution that's given by a junction, so we can just apply that to every element, and then we get some H cell, and that's going to be such a diagonal. That's what we call a diagonal H cell. So in the example here, that would, for example, be the one corresponding to S and STS. Okay, so now I construct a new 2 category by first killing all the cells that annihilate my 2 category, my 2 representation anyway, right? So I fixed my apex, and everything that's not less than or equal to this apex acts by 0 on the categories via my 2 representation. And so I just kill those. Then inside this quotient, I take the 1 morphisms in this H cell, and they will all have the same source and target. So they're all in some fixed CII, and then I add the identity on that as well, because I still need a 2 category. And by the cell combinatorics and the fact that we've now, by quotienting out, forced our J to be maximal, this is actually closed under horizontal composition, and so this is now a 2 category. And then we find the maximal ideal that doesn't contain the identity on these 1 morphisms. So that's our 2 category CH, and that's now much, much smaller. Yeah, so going back to our example, this now, if I pick this H, then I have, rather than having 8 indecomposable 1 morphisms, I now have 3 indecomposable 1 morphisms, namely the identity, S, and STS. And I mean, this is sort of still, a small example. Yeah, 8 doesn't seem so much bigger than 3, but if you go to bigger types, then the reduction is much bigger. Oops, sorry. So then the reason why this is important is because we get a bijection between the simple transitive 2 representations, which have apex J, those were the ones that we were interested in, and the simple transitive 2 representations of this much smaller 2 category, which have apex H. Yeah, so this is a vast reduction because we can concentrate on much smaller 2 categories with a very simple cell structure, because CH will now only have at most 2 cells, namely H and possibly the identity if it isn't in H. And so we call that the H cell reduction. Okay, and now the other thing the other big ingredient that we need is a double centralizer theorem. So if I now take a simple transitive 2 representation of my CH, then of course I have a canonical 2 functor. I can look at the endomorphisms of my two category. Those form a two category again, and and of course the endomorphisms act on my two category, on my two representation, and I can look at the endomorphisms over the endomorphisms. And of course, by definition, because every endomorphism here commutes with C, well, C commutes with any of these endomorphisms. Yeah, so this is a complete tautology that I have this two functor. But now we want a double centralizer theorem. And well, the obvious double centralizer theorem doesn't quite work because we somehow need to kick out identities. Yeah, so we have to restrict, rather than just looking at endomorphisms over endomorphisms of M, we have to restrict to those which give injective endofunctors on the abelianizations of these. So that's a very technical condition. So we have to restrict to a certain sub thing here, and we can only take at H here. So we can't necessarily get the identities, but then these don't have identities, but they are two semi-categories, and they're equivalent as two semi-categories. So this is somehow the best categorification of a double centralizer theorem that you can get here. And that we want to use now so those ingredients, H cell reduction and the double centralizer theorem, we want to use to get simple transitive two representations for Soergel bimodules in finite Coxeter type and in characteristic zero. Yeah, so I'm not making any claims about anything wild here. Okay, so how do we do this? Well, so firstly, we can do H cell reduction. So it suffices to get the simple transitive two representations for SH, where we pick one diagonal H cell in every two-sided cell. Yeah, so that's what H cell reduction tells us. And then to that SH, you can associate an asymptotic bicategory, where, so somehow, roughly speaking, we take the two subcategory, which is generated by those bimodules which have tops in non-negative degree, and then we kill the ideal generated by those which have tops in strictly positive degree. Okay, so that gives this asymptotic bicategory. So this is, I mean, this in different descriptions somehow is due to Lustig and Elias Williamson. And this categorifies this asymptotic Hecke algebra. Yeah. So just like the asymptotic Hecke algebra had no Q anymore, we'd gotten that by taking the Castellan-Lustig basis and in the structure constant sending Q to 0, so Q is gone. And similarly, because we've somehow picked one layer in our filtration, this is now not graded anymore. Yeah. But it has the great advantage of being a fusion bicategory. So this is semi-simple, and it's really well understood for almost all H cells. In particular, it's understood for Weil groups of Weil type, and so there are only a few H cells in Coxeter types H3 and H4 where this is not understood. And by understood, I also mean that there is a classification of simple transitive two representations of those. So those are somehow much better understood by categories. Okay, so now we go back to our SH and we take the cell two representation associated to that. Then we can throw our double centralizer theorem at that, and we get this funny equivalence of two semi-categories. Yeah, but in particular, we have our at H, which is the crucial thing that we care about, and the key theorem that then makes this helpful is that this index here, this endomorphism ring, is actually our asymptotic bicategory. And now I am ignoring gradings. Yeah, I am ignoring gradings because I don't want to set up all the notation. So technically this here is a graded gadget and it's some free Z cover of this thing. Yeah. So ignoring, so this isn't a fully precise statement. And what we can do with that is we can use this double centralizer theorem in a similar way that you prove that matrix rings are isomorphic to the field, to get the theorem that we get a biequivalence of two categories, where one two category is the one that we're interested in, these graded simple transitive two representations of SH with apex H, so these are all the ones that we want to understand where H varies. And here, this again isn't, I mean, I'm not being super precise about the gradings here. What we mean by that is simple transitive two representations of AH, and for the morphism categories between those, we take the Z covers. Yeah. And then we have this biequivalence of two categories here. And so in particular, that reduces the classification of simple transitive two representations of Soergel bimodules to the classification of simple transitive two representations for these A sub H's, which again, outside Coxeter types H3 and H4 is done. And even for H3 and H4, there are only a handful of two-sided cells where no H cell is sufficiently well understood. And I always forget which ones those are, but there aren't very many. And I suppose that was what I wanted to say. Thank you.
Thanks very much, Vanessa. We're all clapping at home, or knocking, as this is in fact a workshop based in Germany, so that does make sense. Right. So, are there any questions from viewers back home?
Can you hear me?
Yes.
Okay, I had a question about I was a bit confused about your categorification of the asymptotic Hecke algebra, because somehow in my mind, like when Lustig introduces it and categorifies it, he takes kind of like a certain slice of the perverse cohomology, so kind of more changing the monoidal structure instead of in your description. In your analogy, when you say generated by bimodules, should I think like you're modifying two morphisms, or what are you modifying here? I'm a bit confused. Can you explain this?
No. So somehow, I mean, what the original description is, you have these perverse things, yeah, and you multiply them and you get something that you then but you always have to shift back and forth by the A function, yeah. And the point is that when you just think about bimodules, rather than, so your perverse Soergel bimodule BW has top in degree something like minus the A function of that W, yeah. And rather than multiplying them and then shifting by the resulting A function, you can just shift all of them to degree with tops in degree 0, and then they just happily stay there. And of course, you get other tensor factors that have tops in lower degrees, and those are the ones that you kill. Those are the ones that don't make it in your perverse filtration.
I see. Okay, so it's just a different global it's a different global like grading shift.
Yeah, exactly. So somehow we work with our favorite indecomposable one morphisms are not the B sub W, which are these perverse guys, but they're the B sub W shifted down by the A function, and we call those C sub W. And those are the ones that somehow give this asymptotic bicategory without much hassle.
Okay, thanks.
Just to check my understanding on something, you restrict to the injective ones, and I guess I see why the identity is not injective. Are all the objects are projective?
No, so what we do is we work in an injective world. So this is somehow because when we first did this co-algebra one morphism business, so it's just co-algebras are better than algebras. And so you get the co-algebras from some injective abelianization. So our CH, the underlying category, CH of empty set, is just an additive category. And then, of course, every endofunctor of that extends to a left exact endofunctor of the injective abelianization. And we take those injective objects inside that. Yeah, so those are morally, so rather than, so if we work dually with projectives, they would be the ones that are given by tensoring with projective bimodules. And those are the ones that are given by co-tensoring with injective bicomodules. Yeah, so it's just coing everything.
But somehow in this coing, you got rid of the identity functor.
Yes, so that's not because the identity, if you think in the projective world, the identity bimodule is not a projective bimodule. It's projective on both sides, but it's not projective as a bimodule.
I understand. It's a top cell sort of.
No, this is a injective bicomodule, but it's not an injective bicomodule.
Got it. Injective as a bimod. Okay, got it.
Yeah, exactly.
And coming back to your discussion in the break, somehow, since you already mentioned singular Soergel bimodules, so what kind of breaks down if you try to like apply machinery for this like real two category instead of, I mean, the Hecke two category that you were looking at?
That works precisely the same, and somehow, in some sense, that's partly what we use because I mean, for example, originally we only had a proof of this theorem, and even only not as a biequivalence of two categories, but just as a bijection, if we had longest elements of parabolics, and that was precisely because we could go to singular Soergel bimodules, where then the corresponding so if you pass to so you're in a two-sided cell which has the longest element of a parabolic, I don't know, associated to J, yeah, subset J of my simple reflections. Then that we can via this H cell reduction, we can use this to carry this over to the semi-simple category that we then get there. Yeah, so singular Soergel bimodules from that perspective are not any harder. And in particular, they don't, I'm pretty sure they don't have any additional, no, they don't have any additional interesting simple transitive two representations.
Oh, okay. Interesting.
I don't know. I think I'm right in saying this.
You might be able to get new things if you restrict to subcategories, though. I might be wrong about that.
What do you mean by restricting to subcategories?
Like maybe there's an action of singular Soergel bimodules where you, for certain parabolic that don't extend to all parabolics. So for instance, maybe there's nowhere for the monoidal identity to go. You know, so like if you think about geometric Satake, it's kind of like a functor from maximally singular Soergel bimodules inside the affine wall group. So you're only considering maximal parabolics.
Yeah.
Maximal finite parabolics.
Okay. That I would need to think about whether that can happen or what. Yeah. Yeah, that is that. I don't know. I mean, I would need to think about that more carefully. No.
Sorry, Ben. Could you repeat what you said? Some of my internet had a little glitch. I don't know. I didn't hear anything.
I was just saying that, like in geometric Satake, there's like a two functor from maximally singular Soergel bimodules. So singular Soergel bimodules to the affine wall group where you only consider parabolics corresponding to the finite wall group and its conjugates. And then to some kind of representation 2 category, that this functor does not extend to other parabolic subgroups because there's just nowhere for it to go.
Okay, thanks. And I have another slightly, I mean, it's not directly related to your talk, the question, but I remember that you have some nice results about distinguished involutions and kind of distinguished involutions giving Frobenius objects and certain subquotients. Do you work in this H reduction for this, or in which setting do you work to prove this? Or like...
Yes, that only works in the H reduction, in this S sub H, in the H reduction. So the de Flow involutions are Frobenius algebra objects or algebra 1 morphisms in these H reductions, but we can't prove that they are that in all of S.
But do you believe this is true or not? Because this is like, I think, a conjecture that was formulated by somebody. I don't remember who precisely came up with this.
So I don't remember. I was going to say I have no idea, but maybe Daniel remembers. Daniel, do you remember? You did some calculations.
No. The only thing the calculation is showing is that our argument doesn't work.
Ah, okay.
That's it. So I would still conjecture that they are Frobenius in the whole category. But
yeah, I just suddenly I was going to say I have no idea.
So in type A, I don't know if you know of an easier proof in type A, but in type A, we have to prove this as part of sort of categorical diagonalization. So
yeah,
there's a proof of the most important part of this fact inside Elias Hogenkamp.
Yeah, no, I just suddenly had this memory of Daniel doing some computations, but it was they only showed that our method doesn't work. So to prove it in general.
But Ben, it's not explicitly spelled out near categorical diagonalization, right? So
no. We were going to write
something to do.
We never got around to it.
Okay, I see. Because it's very interesting, because even in positive characteristic, I mean, I've not done a lot of calculations, but I have a characterization of p-distinguished involutions. And for example, in B2, it's relatively easy to see that in these 2 cells that split up, that in the string that splits up, BSTS is a new p-distinguished involution, and it is Frobenius in the whole category. So I don't know, but yeah, I don't have enough calculations to really, but it's definitely a very interesting question, I think, there.
Perhaps at this point, we should stop the recording, and I'll just mention to people that we have about an hour's break. We'll start in again in 55 minutes.